examples. So we have reached the end of this section. So with this next, with the 3 examples that we have that we are going to see today, the section will be concluded. Now before we go to the examples, let us take a very brief look at the things we have seen in this section. So in this section, what we did, we started off with a field f which was given to us, and over f we considered a non-constant polynomial fx, and we asked the question whether there exists an extension E of f in which fx has its roots. And now we know that such extensions always exist, no matter what field f we are taking and no matter what polynomial f, what non-constant polynomial we are considering over that field. And among such extensions, we also consider those that are minimal in the sense that these degrees are minimal, and such extensions have been called splitting fields of the given polynomial splitting field of our polynomial. That's because over E, f will split completely as a product of linear factors. And on further investigation, it turned out that any 2 such splitting fields for the same polynomial are isomorphic to each other. That too, the isomorphism, the function that gives that isomorphism is such that if we restrict the function on f, then we get the identity function. So that's basically what we have seen in this section. So let us now see what the examples tell us about all these things. So in the first example, the author starts off like this: let f be any field. There is no restriction on f, it's actually any field, and let px equal to x squared plus alpha x plus beta, where alpha and beta belong to f, be a polynomial in fx. Well, of course, if we just simply say it's a polynomial in fx, that automatically means alpha and beta belong to f. But Herstein, however, he chose to write like this. That's not a very big problem. Now, oftentimes he likes to elaborate more than necessary, which is not a problem at all, because for us beginners that is in fact helpful. So we should not criticize that. Now, if E is an extension of f containing a root, say a, of our polynomial px, then it turns out that the element b, which is defined to be equal to minus alpha minus a, and which is of course in E, is also a root of our polynomial. Now existence of E is, of course, we have already said here, and we already know that such E's exist. Now the thing is that if you find an E in which you have found one root, then you can find another root which looks like this. Now instead of just simply believing that this is the case, let us quickly verify this. Let's go through the calculation and see if it is truly the case. Because it's not immediately apparent to me that this is the case, at least to me. So for my own sake, what I'm going to do, I'm going to now try to verify that this B is in fact a root. So I start with this assumption that A is a root. Since A is a root, of Px, so if we substitute A for x in this expression, you should get 0. A square plus alpha A plus beta. And this implies because the root B that the author is claiming is this, that is also in terms of alpha and A. So I think it will be helpful if we express beta in terms of alpha and A. This implies from this equation, last equation, beta is equal to minus alpha A minus A squared. Okay, so that's what we see. I don't see anything else. That's what we can get from the condition that A is a root of Px. Now we just directly try to calculate P of B and see whether we get 0 or not. Now P of B is, at first we just simply use the expression plus beta, and then we write what B is. B is minus alpha minus A, its square, plus alpha times minus alpha minus A, plus, yes, I was right, so this will now be useful, minus alpha A minus A square. So we now expand the square. Doing that, we get alpha square plus 2 alpha A plus A square, and we do the other multiplication also, minus alpha square minus alpha A, and already we have minus alpha A minus A square. So are we getting 0? Alpha squared minus alpha squared, A squared minus A squared, 2 alpha A minus alpha, yes. So his claim is true. Okay, is there any gap in this calculation though? Let us just think about that also, because we are not working with real numbers or complex numbers, but general field elements. So in this part of the calculation there is no problem, because we have used the left distributive law and the other ring laws here. But what about the expanding this square? Does the familiar formula still continue to be true in this general setup? Actually it is true, because you see, this entire calculation is happening where? In the extension field E. and I say E and not necessarily F because we have an element A which is coming from E involved in this calculation. So unless we know that A is in F, we cannot say that this is happening in F. In general it's happening in E, but still E is a field, so it's a commutative ring, and in a commutative ring the general binomial expansion is true. Just like it's true for real numbers and complex numbers, in a commutative ring also it's true. So there is no problem, and B is indeed also a root of our Px. Now two cases arise. So what we are now trying to do is that, fine, we have found two roots of this polynomial Px, and according to the theory that we have seen so far, there can be just two roots, I mean not more than two roots. We have already seen that if we have a polynomial of degree n, then in any extension fields, whatever that extension field is, or even if you consider many extension fields, in any one of them, the number of roots that your polynomial has, counting multiplicities, can be at most n, if n is the degree of the original polynomial. So in this case the degree is 2, so that's why there can be at most 2 roots. But based on the things that we have found here, there will be two cases. These two roots A and B may be distinct, also they may be equal. So let us see the equal case first. Now suppose A is equal to B. So what we are trying to next do now, we are next trying to see how large the splitting field for Px should be, because this E that we are mentioning here, it's just any field containing a root, and in E itself we have found another root also. So E itself may or may not be a splitting field. Yes, it contains both the roots of the polynomial, but it may not satisfy that minimal degree criterion. So we just want to say something about that. So suppose A is equal to B, then using the expression for B, B is minus alpha minus A, from which we will be able to say what alpha is in terms of A. Alpha will be minus 2A. Or alpha is equal to minus 2A. Also, let us also see what happens to beta in this special case. So alpha is minus 2A times A minus A squared. So that means 2A squared minus A squared, so this is A squared. Now let us see what Px turns out to be in this special case. X squared plus alpha x plus beta. So alpha is minus 2A, that means minus 2ax, and beta is A squared. So this is equal to x minus A whole square. Okay. On the other hand, if alpha is if a is not equal to b, if now the roots are distinct, then x minus a and x minus b are relatively prime in Ex. Now, where is this thing coming from? Note that because these are linear polynomials, so they are automatically irreducible over E, because these are polynomials over E. Keep that in mind also, since we don't know whether any one of these two things, A or B, belongs to F or not. In general, they belong to E, so both of them are polynomials in this polynomial ring. Now, because each of these is a linear polynomial, so they cannot be further factorized non-trivially. So automatically they are irreducible polynomials. Now, because they are irreducible, distinctness of A and B automatically tells us that they are relatively prime, that their GCD in this Euclidean ring is 1 or is a unit in the ring E. If you still want to be even more elaborate, you can try to see what would happen if they are not relatively prime. I mean, if you make that assumption, then you will get some sort of contradiction. If you make that assumption, then the fact that they are both irreducible would then leave you with only one choice, that they are associates of each other. That is, any one of them is a unit in the field E times the other, and from that you will be able to derive some sort of contradiction, which however we are not going to do. We just simply state this and we just assume it to be true. Now, by the corollary to, I forgot the lemma number and I don't have it written here also, but you will understand what I am trying to write here. By the corollary to the first lemma, of this section, because A and B are both roots of Px, x minus a divides Px and x minus b also divides Px in Ex. Okay. Now the fact that these two are relatively prime will be used. Because they are co-prime, so these two divisibility relations will now imply that their product also divides Px. And all these things we are doing based on what we already did in the theory of Euclidean rings, and using the fact that this polynomial ring is a Euclidean ring, we can do these things. But the degree of the divisor is of course 2, and the degree of the divisor is always less than or equal to the degree of our original polynomial. Well, in this case actually it's equal, so I should, okay, no, this is not how I should have written it, but the degree of x minus a times x minus b is equal to 2, which turns out to be equal to the degree of our polynomial. Since x minus px and x minus a times x minus b are both monic polynomials, this implies all the things, okay, not just their degrees being equal, but also their monicness and the fact that this divides this, all these things together make us imply that they are equal. So what we have seen is that in this case also, if in the case that a and b are distinct, px has been written as a product of two linear polynomials. In the case when a and b are equal, also px has been completely split as x minus a whole squared, of course, but still linear polynomials are involved in that expression x minus a times x minus a. So the splitting field of px is a subfield of E whose degree is at most 2, because that is the degree of the polynomial. At most 2 we say because we don't really know whether we are having these roots a and b outside of f or actually inside of f. If f itself contains these two roots, then f itself is acting as acting as the stage where this complete split will happen. So we don't actually need to enlarge f at all, and f is the absolute smallest possible extension of f where the degree is 1. So f itself will be the splitting field. So that's why we say at most 2. It cannot, however, go beyond 2. That we know from theory. And we have also seen specifically how the split happens in these two cases. Note one more thing, that the relative primality of these two things based on the distinctness of A and B actually allows us to make this conclusion in this case, which we cannot do in that case where A is equal to B. But anyway, this is our first example. Then the second one. In the second one, we are having more familiar things. Let f be the field of rational numbers. And fx equal to x cube minus 2 be a polynomial over f. Over f or in fx, they mean the same thing. Now here also we would like to say something about the splitting field of this fx. Now before we write anything else, we already should know one thing which we mentioned at the end of the first section itself, which is the fundamental theorem of algebra. What it says is this, that if we have a polynomial fx over the field of complex numbers, then all its roots are complex. Okay, we will not have to further consider extensions of C in order to capture all the roots of f. Further I say, because you already know that C is itself an extension of R, and in that sense C is called algebraically closed. So if one uses this fact and some knowledge of elementary complex numbers, then one can quickly actually find all the three roots of this polynomial, and they turn out to be these. Now we write like this. It's assumed that we know these things. Now we know that cube root of 2 comma omega times cube root of 2 and omega square times cube root of 2 are distinct roots of fx in, let's just mention that also, in the field of complex numbers, where omega is this complex number -1 plus square root of 3 times I divided by 2. Okay, and one can, well, of course, one can just have, given that you have these things, you can just substitute these things for x here, do your calculation in the field of complex numbers, and see that you are, each time you are getting 0, and that just proves that these are roots of this polynomial. What more is there? What about distinctness? You can pretty quickly see that they are actually 3 different complex numbers, so they are distinct. So that means, fine, so the complex field, which is naturally an extension of the field of rational numbers, has all the roots, but that does not say that the complex field is actually the splitting field for this polynomial. That we cannot say. Maybe the splitting field is actually something smaller. So we now need to say something about the splitting field. We know one thing for sure, that whatever the splitting field is, it must contain these three roots. Now, without actually going through the process of systematically finding the splitting field, that is, by attaching these roots to the base field f of rational numbers in steps and trying to find the smallest one that would contain all the three, we are not going to do that. The author has not done that. Instead, using algebra and using the things that we have seen in this section, can we still say something about at least what the degree of the splitting field should be without calculating the splitting field E of fx can be something about its degree. Not one thing, that the splitting field cannot be the real line, the field of real numbers, because already complex roots are there which are non-real. So it has to be something different. So we make one observation here. Note that this extension of f, which you obtain by attaching this cube root of 2, I forgot to say something here, which however I am just simply saying it verbally. It's there written in the book, you can see, where all these things are there, and where this symbol denotes a real cube root of 2, which we know exists from analysis, real analysis. In real analysis, we know that any positive real number has a positive nth root, which is itself a real number, such that its nth power is equal to the original real number, and n is a positive integer. So we are using that fact here. Now note that this cannot be a splitting field of f of x, since this root of f of x does not belong to this thing, but why? That's because this is a non-real complex number, whereas you can see, because your F is the field of rational numbers, so this extension that you see here is a subfield of R. Of course, it contains the field of rational numbers as a subfield of its own, but still it is lying inside R, so it cannot contain any non-real complex number, things from outside the line. So naturally, this itself cannot be the splitting field. Now, so we now invoke that result that we have already seen by theorem in this section 532. We already know what the degree of the splitting field can be. I mean, we can say something about the degree, and that something is this. Whatever polynomial you are considering, it's not necessary that that is irreducible over the base field, but the degree of the splitting field will be less than or equal to, this comes from this theorem, the factorial of the degree of the polynomial, which in this case is 3, because x cube minus 2, and that is equal to 6. So whatever e turns out to be, its degree over f will be less than or equal to 6. But other pieces of information are also there that we have to use. You may find my pace extremely slow. I know you don't say it, but sometimes you find it frustrating, but I do it deliberately because it's better to go slow and be careful than to go fast and make mistakes here and there everywhere. But note this thing, f is a subfield of this extension, which is a subfield of your splitting field E. And now this inequality tells us that E is a finite extension of f. Of course, it's a finite extension of f, it's going to be, and its degree is less than or equal to 6. So if you now recall a result from the first section where we have seen something like this, say you have this. Fields related to one another like this, f, k and e. K is an extension of f, e is an extension of k, and it's given that e is a finite extension of f. Then k being a subspace of e over f, because as a vector space over f, these containments tell us that k is a subspace of e over f. Now k being a subspace of e over f and the finiteness of this dimension tells us that the dimension of k over f is also, that is the degree of k over f is also finite. A subspace of a finite dimensional space is also finite dimensional, and in fact that just that is simply coming from vector space theory, but what we have seen here in field extension theory is that the degree of k over f actually divides the degree of E over F. We saw this in the first section, so that we can use here. But what are the by the corollary to theorem 511? Okay, so by the corollary to theorem 511, the degree of this extension over F divides the degree of E over F, and we know what this degree is. It's rather easy to show that this degree is 3. I leave it to you to understand why it is 3, okay? So what do we see here? We see that this degree can be at most 6, but at the same time it's a number that is divisible by 3. So there are only 2 possibilities. This number satisfying these 2 things can either be 3 or 6. Now, if we consider it to be equal to 3, then what? Then the dimension of this subspace over F is the same as the dimension of the original space over F, which from the theory of vector spaces tells us that this will be equal to this. But which cannot be, since we have already seen that this cannot be a splitting field. Which is not possible. So the only possibility is this. That as a vector space over F, E should be a 6-dimensional extension. So it's taking it's taking on this limit. Do you see that? Because 3 factorial is the factorial of the degree of your original polynomial fx, and the extension, the splitting field that we will have of your polynomial, that should have that value as its degree over f. Is there anything else, any other gap that I may have left? No, I think it's okay. Oh, by the way, do you realize why f cube root of 2 is actually contained in E? That is because E, being the splitting field of our polynomial, must contain cube root of 2 inside of it. So because it is containing cube root of 2 inside of it, and also it automatically of course contains all the rational numbers. So by the definition of this thing, which is the smallest subfield containing f and cube root of 2, this thing should be itself contained in this E, which is some subfield containing f and cube root of 2. Okay, so our example 2 is completed. And finally there is another one which is quite short, because here just simply a claim is made whose proof is not given. The proof is in fact an exercise that we will solve when we solve the exercises in the next field theory video. So we just see, I think I need ink. So in this one, again let f be the field of rational numbers, and let fx equal to the fourth power of x plus x squared plus 1 be a polynomial over f. We claim, and this is the claim that is being made here, we claim that for this polynomial also there will be a splitting field E, and the claim is that this splitting field is actually this extension of f, where omega is of course that complex number from the previous example. Let me also see whether I have really written the correct omega. Yes. We claim that E equal to this, oh, so he keeps on going, is a splitting field of this fx and it turns out that this omega is actually algebraic over the field of rational numbers of degree 2, so that from one of the results that we saw in the first section itself, the degree of E over F will be equal to 2. And this 2 of course is much smaller than the factorial of 4, which is the degree of the original effect. There we got that equal. Here however it's much smaller. Four factorial is 24. So we do not need a 24-dimensional extension. A 2-dimensional extension suffices. Much smaller than the maximum possible. which is 4 factorial equal to 24, and there things end. Let me also remind you of one thing that the author mentioned somewhere among all these things, that this upper bound of n factorial cannot be made sharper. N factorial is extremely large, and it I mean, in the sense that as n increases, it increases at a tremendous rate. 1 factorial is 1, 2 factorial is 2, fine, the increase is not that much. 3 factorial is 6, okay, it has increased somewhat. 4 factorial is 24, 5 factorial is 120, 6 factorial is 720, like that it jumps, and the jump becomes longer and longer. So quickly things become unmanageable. I mean, it's almost as good as saying nothing about the degree. I mean, if you are just simply saying that the degree of the splitting field is less than or equal to n factorial, it's like saying that this room has how many people, how many persons are there in this room, for example. I am the only one here, but I can make a statement like this: there are at most 1000 people in this room. At most, I am saying 1 is less than or equal to 1000, so it's a true statement, but it's a useless statement. But the thing is that this upper bound cannot be improved by making it smaller. That is because that a upper limit is sometimes taken, and the example 2 is one such instance. So with this I end the video today, and this ends this section also. In the next field theory update, we will start solving the exercise problems, and tomorrow we do what? Last Saturday we went through Galilean's group theory exercises. So tomorrow let us go through Galilean's ring theory exercises, and on Sunday of course we have our analysis. So that's just it. I wrap things up here itself. So see you tomorrow with Galilean's ring theory exercises. So until then, this is me, Lucifer, from a mathematical room. Have a nice night.